Hello, welcome to my channel, Tech Talk with Strix. My name is Srikanth Nachiraju. I'm a senior data scientist at Microsoft India. In this particular video, we're going to talk about RAFT for domain-specific RAG. RAFT stands for Retrieval-Augmented Fine-Tuning. It's a paper published in year 2024. Now, this particular approach deals with fine-tuning a small language model or a large language model in a noisy retrieval setting. This is not a paper review, or in fact, it's not a paper summary. It deals with it's more about how and when do you apply this particular technique for your production RAG applications, and how do you evaluate whether this technique is the right approach for you for when you deal with noisy retrieval problems in actual production applications. Now, with that particular context, let's move forward and understand this problem in greater detail. Let's start with understanding the regular RAG in a sense. What is the core capability of a large language model that the RAG depends on? Now, the retrieval augmented generation, or RAG, turns the model into an open book system. So what is an open book system? So typically, when you use a large language model, we can ask it a question which it can answer using its pre-trained knowledge. So as we know, large language models are pre-trained with large corpus of text, which is available in the public domain. And they are further instruction fine-tuned to align their responses to the instructions given by the user. Now, this is the core capability that works today, wherein you can ask a question and it responds with an answer because it's fine-tuned or instruction fine-tuned to align to the instructions given by the user. This is called using large language models in a closed book system. In an open book system, the large language models has not seen the data that we have probably not seen the data that we have sent to it. So what we are asking it to do is, given this particular question and given this particular data that may be new to you, use your reasoning capability or instruction fine-tuning capability to answer the question by aligning your response to the context provided in the prompt. In theory, we are asking the model not to memorize its private knowledge, to go beyond its private knowledge and answer the question in the context of the new knowledge that we have shared. But in practice, what happens is the model's response is only as good as the retrieved context is. If your context is related to the question, you get a right answer because your large language models are good at knowledge and reasoning. But if your retrieval is wrong, you may still get an answer, but it may not be completely right. So how do you deal with this particular challenge? Now, the authors of the RAFT paper divided the failures of RAG into 3 discrete categories. Before I deep dive into those categories, I want to explain a few terminology that is going to be used across this video. The first is called the in-domain. So what does it mean by saying in-domain? In-domain means the language model is operating in a fixed domain setting, and the domain could be a financial domain or a healthcare domain or energy related data, right? So, but we are not going beyond that particular domain. Everything that we ask the LLM is going to be in that particular fixed domain. All the LLMs are capable of going beyond the domain and asking the questions, but this particular paper is only scoped to operating the language model in a fixed domain. We already discussed what open book QA is, and let's talk about Oracle and the distractor documents. So in a typical RAG setting, when the initial first stage of the RAG is the retrieval. You may have heard about the terms like top K, wherein you fetch the top 5 or 6 or 10 documents. Now, within those documents, there could be documents that are relevant to the user's query. There could be documents which are not so relevant to the user's query. So the documents that are most relevant to the user's query are called the Oracle documents. The documents which are completely or partially related to the user's query are called the distractor documents. Okay, so within the failures that can happen within RAG, the first type of failure happens when there is in the retrieval there is an Oracle chunk present. That is, there are relevant documents and also irrelevant documents. So in this case, what happens is the LLM may find the relevant evidence plus the noise. When it's generating the response, it may cite or use the irrelevant document or a wrong chunk. The second failure type could be when the Oracle chunk itself is absent and you have fetched all the documents that you have fetched from the vector DB are the distractor documents. Like your search basically has failed, that it got 5 documents, but all 5 are not relevant. But the model will still be compelled to answer or produce a confident answer in some cases. This is because how the instruction fine-tuning is done for large language models, and in this video I'm going to show you some examples which are related to this particular case. The third type of failure is when you have partial evidence and you have the fragmented facts. In a sense, you have the retrieval, you have the documents which are semantically correlated, which means it has the words that you're looking for, but it is not by domain related to what the user is asking. So it has partial evidence which may not be completely related to the user's question, but it may have some words. So in these cases, what happens is that the LLM may use some knowledge from the context and use some of its previous knowledge to invent the answers instead of generating the answers. So in all these three categories, the common pattern is that the issue is in the retrieval phase, and now it becomes a generation error. You may still ask, can we actually perfect the retrieval? In most of the cases, yes. With good engineering practices or context engineering practices, you can still perfect the retrieval phase, but you may not get the optimum get to an optimal percentage, because most of the times the retrieval is dependent on what the user is asking. And in a production setting, though you can do this in a train and test phases, in production there's no guarantee that it has always retrieved the right documents. So this particular approach that we're taking is going to deal with imperfect retrieval in the production setting. Now, the another way to deal with this problem is about better prompting. Now, let's discuss why a better prompting cannot solve this particular problem. The base models that we're using today, be it GPT or any large language model, they're not specifically trained to deal with bad documents. The documents that the document set of documents that are used during the pre-instruction fine-tuning phase for these large language models are always most of the times good. So they do not know how to deal with bad documents. And RAG specifically relies on this particular assumption that retrieval is always best. So when an Oracle document is missing, the model may overtrust the bad documents, or even at least or use its own memory to deal with the domain knowledge. So it happens even when you use better prompting techniques like chain of thought prompting or asking the model to ground. But in all these cases, we are assuming that the retrieval is always correct. Now another approach to dealing with this particular problem is fine-tuning the model itself, if they are fine-tunable, with a golden data set. Now, in this particular case, they're going to memorize the question and answers, but they do not consider the retrieval at all. So they are only going to memorize the question and answers. They have not seen the out of context answer. They may have not seen the complete domain. They have not seen the. They may not know answers to all the questions. Right? When you go beyond beyond the training data set, you again may see the problem that the model is not able to answer the question. And so in all these cases, the model is learning the answering style, but it's not necessarily learning how to choose the evidence. So from a data science perspective, this is often called a distribution mismatch when you are training the model with certain assumptions in the training phase and testing phase and validation phase. But in production, the data distribution is completely different from what it has seen in the test and the train phases. So how do you deal with this particular problem? So what RAFT solves? Retrieval-Augmented Fine-Tuning promotes or extends the open book exam by combining two different approaches: the open book exam, the RAG-specific instruction fine-tuning, and also supervised fine-tuning, which in a fixed domain setting, which fundamentally means that in a fixed domain setting, when the data is every data that the model is going to see belongs to a particular domain, we're going to fine-tune a model to look at the context and answer the query, and at the same time, the model weights gets updated during this fine-tuning process so that it can also memorize the information. So the model is basically trained in the context that it's going to see during the inference time, which basically means that we're going to train the model with a question and a retrieval document set. Among those documents, there could be one or more Oracle documents, which are right documents, but there will also be distractor documents, which are not related to the question. And we're going to have a response, a golden dataset response, which cites the useful evidence from the retrieved documents, and it ignores the distractor documents or the bad documents. And this particular citation is done in a chain of thought style. So the idea of this particular fine-tuning is that you're going to teach the model to be retrieval aware, in the sense to identify what is the right answer within the set of documents that it's going to see, and ignore any bad documents that it's going to see during the test time. So let's start understanding the outcome of RAFT with the help of an example, right? In this case, we have a question that we're asking three different models. And here's the commonality between among all the three models, right? All three models share the same prompt. So we're going to put the same prompt to all the three models, and we're going to ask the same question to all three models. And all the three models are going to receive the same context, the retrieved context. And in this case, we have fed all distractor documents. That is, none of the documents that we have shared with these models for this particular question are relevant to that particular question. Now, one of the instructions that we have put in the prompt is that if they do not if they are answering the question, also quote from where they have what is the fact used from the context to answer this particular question. And second instruction that we have put in the prompt is if they do not see relevant documents within the context, just say they do not know, right? So if you look at the GPT 4.1 frontier model response, it's mostly valid because it says that since the retrieved documents do not have the data, it says that it doesn't contain the information, so it cannot answer the question, which is expected and valid in most of the cases. If you look at the baseline SLM response, it invented the answer using its prior knowledge. This is something which we do not want to happen in the production setting, because the invented knowledge could be right, could be wrong, but it's not grounded to the facts. We don't know from where it has learned to answer that particular question. The fine-tuned model, the RAFT fine-tuned SLM, the same model fine-tuned with the RAFT approach, answers the query, and it also quotes from what is the line that it has used to answer this particular question. And the surprising fact here is that this particular line exists in the actual document. It will not exist in the context that we have shared to the SLM in this case, because we have purposefully shared all the distractor documents, but it is identified which line within the context is talking about this particular question, because during the fine-tuning phase, it has memorized that particular answer. So this is the exact benefit of fine-tuning the language models using the RAFT approach. So when they do not know the answer, when the context is completely bad, they still try to answer the question using the memorized information during the that I have learned during the fine-tuning process. And having understood the benefits of the outcome of a RAFT fine-tuned SLM model, let's understand how we set up the experiment. So for any document purpose, corpus, here I've taken an open source document called a ServiceNow. It's a ServiceNow operational PDF, and I've converted that into chunks. And then after converting it to chunks, I've given each chunk to GPT model and asked it to generate the question, the corresponding context, and a chain of, and an answer in the style of in the chain of thought style. The context itself, I've set up in a way that it has both the Oracle and the distractor documents for P percentage of the documents. In this case, I've used 80%. And for the remaining 20% of the questions, I've only added the distractor documents. That means none of the documents are actually related to the question. After that, we convert that whole data set into train, test, and validation data sets. You take the test data set and do an inference for this question that you have, and given the context, which could be Oracle plus distractors or only distractor, and then ask the GPT 4.1 to answer the question. And you store the responses in a CSV file. This is basically used later for a comparison. Now, how do you start a RAFT fine-tuning, right? So you take any base model, any base instruction, any SLM model or any model that is fine-tunable, and you may not do a full fine-tuning. You can apply the optimization approaches, like in this case I'm using LoRA. You may also use QLoRA, and then you fine-tune the model. The fine-tuning is pretty simple. You're going to give the question, the context, which is Oracle documents or the distractor documents, and also you give the expected answer, which is the COT answer, which is generated by the GPT-4o model. And then after fine-tuning, you save the model, and then you ask, and then you use the saved model to do the inference on the held out data set, which is the test JSON file. And at the same time, you can also do the inference on the baseline model. So at the end of this experiment, we're going to have the 3 CSV files. One CSV file after doing an inference on the held out data set, which is the test data set. One by doing the inference on the fine-tuned Llama model. And the third one is the inference which is done on the same test data set on a large language model. And finally, we combine these three and see if we have see any significant improvement when compared to a baseline language model. You may also compare with the large language models, but it's not an apples to apples comparison, because large language models typically have way too many weights, which help it to perform better than compared to any small language model. So let's understand in detail how the training setup is done and how the RAFT fine-tuning is done. So there are 4 important aspects of this particular thing. One is the data preparation. So for data preparation, I've used open source PDF document like this. It's related to ServiceNow security based practices. It appears like something like this. It has roughly 45 pages and it's mostly text and visual content. But for this particular example, I've ignored the image data. So I've used this RAFT datagen Python file basically, which chunks the particular PDF into multiple parts, and for each chunk I'm generating the RAFT dataset using GPT 4.0. Once you run this RAFT file, it generates 3 files: test, train, and validation datasets. Now you can use this particular notebook to see how the training data looks like. So I'm going to show you one row here. So the training data appears like this. So every record in the JSON-L has the type, which is the whether it is a distractor, in the sense it has all the data as bad documents. This is the question that we are asking the model, and this is the context. This is the original context, which contains both in this case, since it's a distractor document, it has all the bad documents. In case of Oracle, it may have 80% of them or some percentage of them being good documents and some percentage of being bad documents. This is the original Oracle context. This is actual context, which is actually not passed to the model, but we have used it for reference here. This is the response generated by GPT-4o. So you're going to you're going to tell the LLM model you're going to tell the model that, okay, this is the question, given this particular context, this is the answer I'm expecting, so that it can identify the loss and fine tune the weights to make sure that the response aligns to this particular answer. In general, actually, we are actually passing this particular instruction, which is nothing but the single concatenated string of all the context. Okay, so we're going to have roughly in the training data set of 500, there are 80% of them are Oracle type records, which means they're good plus bad documents, and there are 20% of which are the distractor documents. Now, let's go back and see how the training is done. So once this data is generated, I'm zipping this data and uploaded it to Kaggle. I've generated a publicly available data set that you can also use. So on the Kaggle side, I have two notebooks. One is this notebook, which is used for training, or let's say fine tuning. So in this particular notebook, we have linked to this data set, which is having the same test, train, and validation data set. And in the notebook, it contains a very commonly known steps. So I load the RAFT data set. And this is the data set you can see I've just shown you in the VS Code. And I'm just converting it to a Hugging Face data set, and I'm loading the base model from the repository. Here I'm using Unsloth Llama 3.2, and this max sequence length and all depends on the kind of data that you're dealing with. You can do some engineering to figure out exploratory data analysis to figure out what should be the max sequence length and what should be the max tokens that the model should produce. I'm using a GPT-3 Llama 3.2 tokenizer because I'm using the same model, and I'm constructing. So this is I'm using the parameter efficient training. So in the LoRA approach, I'm going to only train these particular modules of the model. Depending on your capacity and depending on your training needs, you may also add more modules, or you may reduce the models. Secondly, after this is how the prompt structure is going to look like for the model, that you're going to say that you're an assistant. This is the context, this is the question, this is the context, and this is the answer. So I'm expecting the answer in this particular style. So this is the I'm using the both training data set and also using the eval data set, which is nothing but the validation.json file. And once your training starts, you may notice that somewhere here you will see the training start. Yeah. So here in the training phase, you're basically you're basically training that for 120 steps. I'm using a single GPU T4 on the Kaggle, and the batch size is 64. The gradient is accumulated after 16 steps. You can also increase this based on the size of your data, or decrease it if you are dealing with larger chunks. These are all hyperparameters. It may change for you if you're dealing with a different type of data. For me, this combination has best worked. And if you can see, the training loss and the validation loss have consistently come down from 1.0, 1 point something to 0.5. I could have continued this for more. In a real production setting, you should go for more steps and then stop once you see a stagnant or flat line in the training loss function. Now, once the model is sufficiently trained, I uploaded it to the Hugging Face model hub, and then I can pull from there and then do the inference anytime. So here there's some sample inference, but I've also used another notebook to do an inference at bulk, in the sense like I've downloaded the model and I've taken the held out data set, which is a test JSON file, and I generated the SLM predictions CSV file, and also SLM baseline predictions CSV file, which is basically the SLM predictions coming from the baseline model. So after these two notebooks are completely run, you will have three files, which is the SLM predictions file, SLM baseline predictions file, and the LLM predictions file. I've used a different I've used a different file for LLM inference. In this case, LLM inference, I'm using the GPT-5 4.1 model to generate the responses for the same questions that I've asked the fine-tune model to perform. Okay? So you have three files in the final output: the predictions that are generated by LLM model for the same test data set, the predictions that are generated by the baseline SLM model, which is non-fine-tuned Llama model, and SLM predictions is basically the SLM fine-tuned, RAFT fine-tuned SLM, which has generated the answers for the questions. You can merge all these together using Python file that I've built, which is Llama evaluate. And finally, you have the final results, which is a combination of wherein we can notice these significant difference in how the model performance has changed before and after fine-tuning. So after the fine-tuning is completed, like I said, you have the 3 CSV files. Here we're looking at how did each of this model perform after the fine-tuning. So here I'm showing the random oracle quotient, which is like a little set of documents that have both the distractor and the oracle context. So here in this case, the question is when should a case be marked as security case, right? And these are the retrieved documents. These are actually, I cannot say from here which is the right document or bad document, but assume that among the four documents, a few documents are the good documents and a few documents are the bad documents. So here is a GPT 4.1 answer. Like we all expected, it's going to give you a right answer because it's a large language model. So it's going to quote the answer, quote the fact from the context, and also answer in the style that we are expecting. This is the response format that we were expecting. It's perfectly aligning to that particular response format. However, if you see the baseline SLM model, which is Llama 3.2 model, it has, first of all, not adhere to the response style. It gives you a very elaborated response, and there is no answer tag in a sense. It's not even a complete answer because it has reached this max token length. So this is not a usable answer. So the outcome here is that if you use a small language model that is not instruction fine-tuned, you cannot use it in this particular domain for a simple RAG approach. Now let's look at a fine-tuned SLM, right? So the fine-tuned SLM has perfectly aligned to the style of response. It has used the step-by-step reasoning step that we have asked the model to. We have asked during our prompt in the prompt, and it basically understood the question. It located the right information. It has put the right information in the code, and then finally provided an answer in the answer tag. Okay, so here in the sense, like the outcome of this particular for at least reviewing the Oracle data is that we can bring a fine-tuned SLM closer to GPT 4.1 if you have the right data set, golden data set, and you fine-tune it with the right fine-tuning tactics. And the baseline SLM cannot be directly used in typical RAG settings. In this case, it's a 1 billion model, so it did not perform well directly in a smallest database. They both GPT 4.1 and fine-tune SLM align to the required response format, and we see a significant deviation in the baseline response that it could not even answer the particular question. This is a good qualitative measurement that RAFT fine-tuning improves the focus towards finding the related evidence from all the contexts that it has seen. Remember that it has actually seen both the good context and the bad context. No, the important aspect of this particular thing is how does the model respond to distracted questions, right? In this case, I'm asking a question and I'm passing all the relevant documents to the model. As you can see, there are 4 documents which are not completely relevant to the question, and the actual relevant response to the context is here. Let's see how each of these models have responded. So GPT 4.1, the question here is what features does the AI agent offer for managing AI agents? So GPT 4.1 has aligned to the response format, and it says that the retrieved documents do not contain information. Features offered by the AI Studio, which is expected and which is good to know that okay, it did not get distracted by the irrelevant documents that we have shared. In the baseline SLM, however, it has not followed the response format and neither answered the particular query, which is expected because it could not answer with the right context. Without the right context, it's not going to answer the question anyways. The interesting aspect here is how the fine-tuned SLM answers this particular question. Here, if you see the answer, it actually aligned to the right format, and it also answered the question in this case. It says the AI Agent Studio offers features such as AI management, AI monitoring, and AI agent reporting for managing the AI agents. Now, the interesting aspect of this, and it also quotes that particular line that it has seen in the context, is this is never shared with the model. From where is it getting this particular information? And in this case, it is the right information. Now, if you notice, this is the fact from the document that we have used to generate the data. It actually maps correctly to the actual facts within the document. So during the RAFT fine-tuning phase, the model not only learns to identify the right answers among the distracted documents, it also memorizes the responses in case of no right responses. In case of the golden data set, like if you have a question answer pair that is having this particular question and the right answer quoting the reference, then it also acts as a supervised fine tuning. So in a RAFT, you're combining the supervised fine tuning plus the identifying of the right documents. So it works in both the ways that when it doesn't find the data, it also uses the internalized information to give the response. Having understood all of that, let's see when to use RAFT. So you can only use RAFT when you have a stable domain corpus, right? So because you're using the domain data you're teaching the model to adapt to the domain as well as to identify the right documents, you can only use within the fixed domain. If you teach the model to align in a particular domain, it's not necessary that it has generalized to learn across the different domain. You cannot use the same model in a different domain setting. It may learn to adapt to noisy retrieval, but it may not be able to answer the questions that when the context is completely wrong. You can, this is only helpful when your retrieval returns semantically close with noisy chunk. If your retrieval is perfect and you're very confident that even in the test production settings your retrieval has no challenges, then draft will not help you much. You can only use this with smaller or cheaper models in production. You need a very, if you can use this only if you need a smaller or cheaper model in production, and says that like if you want to replace your large language model with a smaller or cheaper model, or if you want to improve the performance over the large language models, if you notice that the retrieval is bad at some point. Like if you've seen, there's some examples that I'm going to show wherein you see that large language models confidently lie when the context is bad. So if you notice such examples, then this is the right approach. You care more about grounding the answers, that you need that auditability in the responses, that this is the fact that I've used to answer the response. And in that case, even in the imperfect retrieval settings, then RAFT is the right approach for you. Most importantly, whether you can generate the right Q&A answers. In this case, I've used the large language model to synthetically generate the Q&A, but it still needs a human supervision to ensure that the answer it has generated is in fact correct. Right? RAFT is strongest when the retrieval distribution at training time resembles the production retrieval. Like in the sense, like you see in the training time you have perfect plus imperfect documents. Even in the production, if you're expecting perfect and imperfect documents, then RAFT is a better approach for you. Now let's look at a sample that demonstrates that bad retrieval, the RAFT doesn't fix the bad retrieval, right? In this case, this is a distractor question, and which means that there's a question, and there's a question like this: why is it important to establish security hardening priorities? And none of the context which is shared to the language model, which is GPT-4 and SLM, are relevant to that particular question. So these are all the bad documents that are shared, and in fact, the actual right document is never shared with the language model. Now, if you look at responses from each of those models, like GPT 4.1, it is compelled to answer the question because some of the information that is available in the data relates partially to the security hardening priority. So it has this word security hardening somewhere in the context. So the GPT-4 immediately assumes that it relates to the question and then answers the question using its prior information, as well as assuming that the information that is given in the context relates to it. Now, if you look at baseline SLM, as we have seen, we can completely ignore this because it will not be able to answer this directly. And if you also look at the fine-tuned SLM answer, it is also compelled to give you the answer, assuming, but here in this case, it's quoting the context which is shared with it and not using the previous prior knowledge that it has learned from the fine-tuning process. Here, it is still quoting the MID server security hardening priorities, whereas the actual data that it needs to quote is related to not to the MID server. In fact, it is related to something there's a different section that talks about security hardening settings from where the question was in fact reverse engineered and created. So what this means is when you have a bad retrieval, that is, you have data that contextually or by words align with the question, but functionally it's incorrect. And this is the most common case that we see in production RAG setups, where you have retrieved something because the word matches, subword matches, or semantically there are common words, but it's functionally, but the domain wise, it's not relevant to that particular question. Both the language models, the SLM, the large language model, frontier models, and the fine-tuned SLM are compelled to answer incorrectly and by quoting the incorrect examples. So what are the limitations and risks of this particular approach, right? The quality of, as we know, quality of this whole approach depends upon how good the labeled data set is. So in this case, I've reverse engineered, but in the production setup, it is recommended to have a human reviewer to validate the question and answers that are used to feed or train to the model. Bad Oracle selection teaches bad evidence behavior. In a sense, if you have the Oracle documents which you think are Oracle, but they're actually bad, then you are going to teach the model incorrect behavior. The models will become stale if the domain evolves. In the sense, if your domain is introducing new rules, new business rules, or new terminology, the model doesn't learn it. Though it may work at sometimes because it has learned to identify the right context from the retrieved context, but it cannot further internalize the information. So if the retrieval is not perfect, then it won't evolve as the domain evolves. So if you have a very fragile or very the dynamic domain that evolves very frequently, this approach may not completely solve the problem. Fine-tuning doesn't replace the retrieval evaluation in the sense you still have to evaluate your retrievals, whether your how perfect your retrievals is given the question. It's not that we're completely absconding the retrieval problem. We still have to evaluate and perfect the retrieval so that your answers are more aligned and correct to the question that is asked. It may be difficult to answer long context and table questions in the 1 billion parameter model, but this is more of an example. So you can go for a little larger model like 7 billion parameter model. Domain adaptation can reduce generality outside the domain. So in this case, it's a fixed domain setting. So it's you're going to when you adapt this more closer to a domain, we lose certain generality of the model. So if you ask a question outside the particular domain, you may see that it's not so relevant. It may not provide the answers as relevant as it used to do before. So RAFT does not solve irrelevant yet semantically correlated retrieval. Like I mentioned, the last failure in the example 3, if your retrieval is semantically correlated or lexically related, it may still think that okay, this is the right document and ground the response to that particular context. It won't be able to identify that okay, it's an incorrect the incorrect retrieval. It won't solve, and RAFT will not be able to help if the retrieval itself is incorrect. So overall, RAFT improves the generator, but the full rack system still needs retrieval monitoring even in the production system. But given that you have imperfect retrieval in the training and the test setups, and given that you have a fixed domain, RAFT may definitely improve what you see in production. And in some cases it may be better than the LLM if you have a better quality of the data set, and if you have the right combination of bad and good documents, and if you have perfectly trained, you have trained it for enough steps so that it aligns to the domain, and it also learns to identify the good and bad documents. So it's given all this particular setting, then you may see it definitely benefits in using the RAFT approach in the production setup. So summarizing the whole thing that we have learned in this particular video, so regular RAG often fails because the retrieval context is noisy or incomplete in a production setup. Standard SFT, when you use standard instruction fine-tuning of a small language model with golden data set, it performs poorly because it has only learned to memorize the information. It has not learned to identify and build on the new information. So it answers better when it knows it is the sample from the training or the test validation data set, but if you give a new information, it won't be able to answer the query. RAFT trains the model to learn the evidence selection or use the domain information. So in both the ways it may work. So if it in the production setup, if it is given a right and a good and bad documents, it learns to identify the good set of documents. If it doesn't see any good document, it's a completely irrelevant context, and it tries to use the domain alignment to answer that particular question. We have also seen that a small language model's behavior can be brought near to a large language model given a fixed domain and a very good training data set. And we also learned that RAFT can only be used if your domain is stable, in a sense if it's and the retrieval is noisy, and cost matters, right? So if you do not have a stable domain, if you want to use this RAG in a different domains, or if your retrieval is already correct and you want to build on the versatility of the large language models, RAFT may not be a right fit for you. The last step is the number of distractor documents that I use during the training. It is mostly a domain dependent thing. Here in this case, I've used 80-20%, but depending on the complexity of the domain, treat it as a hyperparameter and then experiment with multiple combination of distractor plus Oracle documents and see what's right fit for you. So if I want to summarize this in a single statement, RAFT, from a data science perspective, RAFT is an attempt at reducing the mismatch that happens between the training and the inference time for RAG. In a sense, if you have in the training, the model is always seeing the good documents, but in the testing phase, in the production phase, it's seeing good and the bad documents. So there is a significant difference in the data distribution between the training and the production phase. So RAFT helps in aligning the model to learn that particular mismatch and to train in those circumstances and be ready for production so that it can identify the good documents among the among the overall context. So that's all I wanted to talk about in this video. Thanks for watching and have a nice day.